And that despair that Ross spoke about is palpable in the climate science community. I was at a geoengineering workshop, actually, in November at Harvard. Some of the top American climate scientists were there, about 30 people. There were 2 Canadians. I was one of them. And the reason, as you pointed out, the reason that they're starting to think about geoengineering now is because we're going fast in exactly the wrong direction in terms of our carbon emissions globally. And so they're saying mitigation isn't working. We're not cutting carbon emissions. We have to start thinking about Plan B. Plan B may be pumping millions of tons of sulfate aerosols into the atmosphere of this planet to try to reduce the amount of solar radiation coming to the Earth. Now, every single one of those scientists recognized that this is a staggering gamble for the future of the biosphere, that there may be untold unexpected consequences and things could go horribly awry. But if Greenland starts to melt, and we're looking at a 5-meter sea level rise, or more perhaps over an extended period of time, then people may start demanding around the world geoengineering. The concern that I have, just on this geoengineering issue very quickly, is that in 20 or 25 years, when you're about my age, geoengineering is liable to be on the table because there don't seem to be many alternatives at that point. Now, I think we still do have some choices, but they're rapidly dwindling. So I want to give you a sense for some of this climate science. I'm going to fly. I'm going to go fast, and then I'm going to say a few words to reinforce what Ross was talking about in terms of the seriousness of the coming social transitions we're going to make, the kinds of social disruptions that are likely to occur, and what especially young people can do. And then we'll have an interesting conversation, I hope. What you're looking at here are NASA data for 2007. This is a map of the world showing climate or heating anomalies against a baseline of temperatures from 1951 to 1980. So that's the average that's used. And across the bottom, you can see the warming from 3.5 to 4 degrees Celsius. This is 2007, so this is the second warmest, tied for the second warmest year on record. And you notice that there's very substantial warming in the north, and that's something that I will come back to in a few minutes. It's a very important point. This is a long-term trend line for temperature increases, mean global surface temperature, going back to 1880 across the bottom up to 2007. Every one of the square dots represents a year, the mean global surface temperature for that year. You have dotted lines between the dots. You can ignore those. The 3 green lines are uncertainty bars. The red line represents the smooth 5-year average. That's what you really should be paying attention to. The Earth's climate is chaotic. From year to year, it varies around the trend quite substantially. It's that chaotic response is largely driven by what are called ENSO events, El Nino Southern Oscillation events, which is a kind of sloshing of water and heat back and forth in the southern Pacific Ocean that affects climate around the planet. When you have an El Nino event, you tend to get warmer temperatures globally. When you have a La Nina event, as we have right now, you tend to get cooler temperatures. 1998, which is that spot right there, was El Nino of as large as any we've seen in the last century. We're now in a La Nina phase, which is why we're getting a cold winter this winter with considerable amount of snow in much of the world and cold temperatures. One of the things that you're going to see, and you are hearing out there in the blogosphere and among the climate skeptics right now, is the claim that global warming has stopped. What they do is they look at the last cluster of points and they draw a straight line through them. Now, any of you who've taken statistics knows that is somewhat illicit. You choose your data points, you can draw straight lines all over the place here, and it's essentially meaningless. Climate is a long-term phenomenon, and it's a result of averaging over many years. We happen to be in a La Nina situation. We happen to be at a solar minimum in terms of the amount of radiation coming from the sun. There are no sunspots on the sun right now, which means that there's about 1/3 of a watt per square meter on the surface of the planet, less solar radiation. And so temperatures are a bit cooler. It's likely that solar cycle will kick in again and we'll start seeing an increase in solar radiation, and we're probably going to flip in the next year or so back to El Nino the El Nino part of the cycle. And the expectation is that about 2010, 2011, we'll see temperatures higher than the record in 1998. If we're looking out to the future using IPCC estimates, which are now probably conservative, the scenario that is a particular concern, or the one that is often used as sort of business as usual, is this one called A1b. This is a scenario representing a certain population size for the human population, certain kinds of technologies, certain energy usage rates, certain trade between rich countries and poor countries. A1b is considered a mid-range business as usual scenario. Across the bottom, we're looking from 0 degrees Celsius to 8 degrees Celsius. These are the range of temperatures that we get from 2020 to 29. A little bit difficult to see here. This is 2090 to 2099 within the lifespan of your children. We're looking at increases in temperature. Again, this is conservative within Canada of up here, 3 to 4 degrees Celsius in much of the habited part of Canada, 5 degrees in northern Canada, and 6 degrees Celsius or more in the Arctic. Just to give you a sense for the magnitude, the total warming of the planet since the coldest period of the last ice age, 15,000 years ago, is 5 degrees Celsius. This is a very rapid change. In fact, we're going to drive in this century the temperature of the planet, the average temperature of the planet, higher than it was during the last interglacial period, 125,000 years ago. And in that last interglacial, about 2/3 to 3/4 of the Greenland ice cap melted, and sea levels were 4 to 6 meters higher than they are right now. Now that's a long-term process, that melting, but we seem to see things happening in the Arctic right now that are of particular concern. This is a map of Arctic ice from the National Snow and Ice Data Center in Boulder, Colorado. This is pretty close to the sea ice minimum this past September, 9th of September 2007. That's the actual extent of sea ice in the Arctic. The magenta line represents the average extent of sea ice from the period 1979 to 2000. So compared to that average, we lost about 1/3 of the sea ice this past summer. And if we want to compare it to the 1950s average, we're down about 50%. These again are National Snow and Ice data, and the National Snow and Ice Center data. What we're looking at here are across the bottom from 1978 to 2007. Here's millions of square kilometers of sea ice in the Arctic. Each dot represents the minimum extent, usually about mid-September, of sea ice. You can see that they've regressed the line down here and found a pretty steady trend. The key thing to notice, of course, is what happened in 2007. It's unclear. We only have 1 year of data, but that change wasn't expected, according to the models, for another 25 to 30 years. The IPCC said that we would lose all the sea ice in summer in the Arctic probably around 2060, 2070, 2080. A year and a half ago, based on what was happening just in the last couple of years, scientists were saying 2040 or so. Now they're starting to say we'll see complete disappearance of the sea ice in the Arctic by around 2015 or maybe earlier. What we may be seeing is the first macro, nonlinear shift in a major feature of the global climate as a result of human-induced climate change. This is a flip, right? You've probably heard about the possibility of climates flipping. And what we're seeing, perhaps, is a flip in what's called the cryosphere, which is the system of ice at both ends of the planet, the North Pole and the South Pole. You might say, oh, what does it matter? This is ice. It's a long way away from us. It's what, how much polar bears are going to drown. It doesn't really matter that much. And I get that response a lot. But above the Arctic Circle, the area above the Arctic Circle represents about 9% of the total area of the surface of the planet above the equator. You change that from a highly reflective surface to a highly absorptive surface, and you start changing the energy balance for a significant portion of the planet. And that affects things like the jet streams, storm tracks, and potentially food production in places a long way away. This is a very serious matter. When people talk about melting the sea ice in the Arctic, and they start talking about things like, losing polar bears, or gee, we're going to have fights over whether we can get freighters through the Arctic, and we're going to be exploring for gas and getting into fights with other countries for exploring for natural gas and oil. Believe me, if we lose the sea ice in the Arctic, we're going to be thinking about a lot of other things besides property rights in the Arctic.